is my pleasure to introduce Professor Celeste Kidd, who is Assistant Professor of Brain and Cognitive Science at the Center for Visual Science at the University of Rochester. She is the primary investigator of the Kidd Lab, the director of the Rochester Baby Lab, and the co-director of the Rochester Kidd Lab. Her research broadly centers on cognitive science, psychology, and computational models. She'll be speaking to us about computational models of curiosity. Thanks. Yes. Thank you very much.
Thank you guys also for having me speak here today. I'm very excited to talk to people from such a diverse set of backgrounds. So today, I'm talking, like Perry said, about computational models of curiosity. This is a topic that my lab works on primarily. In particular, we're interested in curiosity as a process for driving knowledge acquisition, including language acquisition. So you can think of an adult and their mental all of their knowledge as being a sort of mental representation of how things operate in the world. They use that understanding of how things operate in order to make decisions. The more accurate their mental model of how the world operates, the more accurate the simulations they can run are, and the better decisions they can make. The problem is, and what my lab focuses on, we know that what you know shapes what you're interested in. Infants know very, very little. So a primary question that I'm gonna start by addressing in a place where my lab started with this work is understanding how infants in particular start their quest for information, how they start to begin building up a big adult-like representation of how things operate in the world, because that's going to be so crucial for everything else. So I want to start by showing you guys an experiment that we designed to look at this. I'll talk you through it. So it's going to start with an attention getter. This was an experiment that was done on an eye tracker. This is an attention getter, and as soon as infants were looking at the screen, we started the displays. Can you guys hear that okay? Okay. So each display has 3 boxes in 3 unique locations with 3 unique things inside. And as long as the infant kept looking, then the display would keep unfolding. These displays, okay, so when the infant looks away, the attention getter comes back, and they get 3 new boxes with 3 new objects and 3 unique locations, and again, it starts unfolding. And what we were interested in here is what drives infants' interest. So at what point do they look away, and at what points do they decide to continue looking, and how is their interest and attention driven by the information theoretic properties of what they're seeing? I'll show you guys one display. One thing to notice, hopefully you get the intuition that some events are less exciting than another. Like if it's a lollipop again, that's not very exciting. I was like, I knew it was going to be a lollipop. Whereas other ones are much more exciting. So the point here is we randomly shuffle the boxes, the objects, and the locations. And what we're interested in is how infants' interest relates to where things occur in the sequence. Here, let me show you, this is a video of an infant looking at a display. So as long as she looks, it keeps playing. And you guys can hear it okay? So the music keeps playing, she keeps watching. We're waiting until she looks away for 1 second. That one was very exciting. Mom is less excited. Okay, she looks away, display turns off, attention getter comes on, she resets, and we do that over and over again until the baby gets bored, or more often the parent gets bored. Right, so this is what the data that we collected looks like, and what we do with this is we use these displays to measure when infants terminate their attention. We represent their expectations about what's likely. These are going to be probabilistic expectations about what's going to happen next using a computational model. What we were expecting to see is, like previous theories have predicted, that there's a U-shaped relationship between information and interest. And I'll come back to that in just a second. So I'm not going to go into the details of the model too much, but I'll walk you sort of the intuition through the intuitions behind it. At each point in the sequence, something happens. Let's say that you're the baby and you've seen 3 A's and a B. So you've seen mostly A's and B's. But your observations are not the only thing, the only way that you generate expectations. Before any of the objects started popping up, if I showed you just 3 boxes and I said, how often do you think it's A versus B versus C? Most people have the intuition that you think that they're all equally likely. So that we represent with a prior belief. So you combine the observations with the prior belief and get some sort of updated belief. In this case, if you'd seen 3 A's and a B, and you want to know what how predictable or surprising the next event is, you use this updated belief to assess that. So at this point, you think it's mostly A's, less often it's B's than it's C's. If you were to get another A again at this point, well, that's what you thought it was. That's not super surprising. That would go towards this end of the spectrum. We'd say that that's a predictable event. If, however, at this point you got a C, you didn't think C's occurred very often, that's toward the other end of the spectrum. That would be very surprising. If it's something in the middle, you thought it was B sometimes, but not all the times, that's a middle amount of predictable. With these U-shaped theories, we're predicting that those are the kind of events that infants would find the most interesting. And I'll skip and jump straight to the infant data. That's exactly the pattern that we see. So this, again, is the model's the model's measurement of how predictable or surprising an event is in sequence. And this is infants' probability of looking away based on the surprisal measurement. So infants are very likely to look away when things are very, very predictable. So that's like that lollipop, 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 lollipop 100 times, you get a lollipop again. And they're also very likely to look away when things are very surprising. So if it was a lollipop 100 times and you thought that no other event occurred and then you get a plane, that's very surprising. And that kind of look away also, that kind of event also triggers a look away in infants. Where they're least likely to look away, they're most likely to stay engaged, is those events of intermediate surprisal. So things that are a little bit surprising, but not overly surprising, are what infants find most engaging. If that was the case just in that one type of display, that wouldn't be very interesting. You might also be wondering, for the displays I showed you, maybe you don't just care about how often A versus B versus C, but the transitional statistics as well. So given that I just saw A, how likely is it to be A again versus B versus C? For a transitional version, I was like, you get exactly the same effect. You get this nice clean U-shaped function. We've also seen that this is true for different types of displays, not just visual displays, but also for auditory sequences. Infants are preferring to stay engaged for the intermediately surprising events. You might also wonder, is this an effect that's just because there's maybe 2 types of infants? Maybe there's infants that prefer very surprising events and infants that prefer very predictable events. You average them together and it looks like a U, but they're not really a U. We've done other analyses where we're able to recover a U shape not just across a population level, but within individual infants. So this sort of preference for intermediately surprising events is evident in individual infants, although how surprising they prefer things, there is some variation. These sort of look all symmetric, but the axes are different. I'll come back to that at the very end if I have time. I forgot to ask too. I was like, I don't see a clock. Is there a? I was like, what time should I wrap up? And I'll keep an eye on it. I forgot according to the schedule. Sorry to put you on the spot there. 1:40. Okay, great. Oh, we have so much time. Okay, great. Yeah, so I'll come back to this at the end. So I was like, hopefully I've convinced you so far that infants appear to have selective attention. Yep. That could, oh yes, yeah. I was like, I knew. Yeah. Infants have a selective attention for events of intermediate surprisal. It's robust to display type and the modality of the stimuli, and it's robust within individual infants. Why this is important is because even infants that know very little about the world are playing a very active role in sampling. They're picking stuff that's ideally suited for learning. I went through really quickly that there were previous theories about why the U. I want to go back to that. I'm going to address that again. The U maybe is somewhat surprising. I was like, on the end where things are very predictable, that intuition is maybe clearer. It makes sense that if things are not very surprising, they don't offer any new learning value. These U-shaped theories are based in the idea that infants should seek out stuff that is good for learning. If you were to imagine yourself picking out some new learning material, you guys probably all know your ABCs. Maybe you encounter this Sesame Street video. Maybe your kids made you watch it 100 times. If you know all of the material in it, there's no new learning value there because you already have those mental representations fully formed. So this end of the spectrum, it makes sense why you disengage from stuff that's very predictable. It's overly redundant with what you already know. You're not going to get any learning value out of that. On the other end of the spectrum, that's the one that I think requires more explanation. So you might think that the more new information you have, the better. But if you go too far the other direction, let's say you pick out this DVD in a language you don't speak on a topic that you don't speak, aviation, that's a lot of new information. You could potentially learn a new language and you could learn a new skill, but hopefully most of you have the intuition that that is not a good idea. If you were to try to acquire all of that at once, you wouldn't get very far. If you knew the language, you could acquire something about the skill. Maybe if you knew a lot about the skill, you could acquire bits of the language. But trying to acquire them both at once, the intuition is that it's not tractable. You're missing the base levels of representation to make sense of this. That's the intuition behind those old U-shaped theories. The idea is that you should prefer stuff that's in the middle. Things that are a little bit surprising could signal to you that you have the basic components needed to make sense of them, but you're also learning something new by nature of it being surprising. So that's where we started. Where we've moved since then is looking at how that mechanism could interface with the complex dynamics of real-world learning situations. The situation that I just described to you is one where we're attending to one stream of statistics at a time. But if you think about any real-life stimuli that exists in the world, like, for example, language, it's sort of hierarchical. There's layers of statistics. If you think about just language, I could be caring about the statistics about the sounds or the syllables or the words, or the phrases or the sentences, or things even above that. So how does this work in real-world learning situations? Another direction that we wanted to move in was relating these low-level sort of biases directly to learning. The pattern that I just showed you shows that infants exhibit a pattern that was theorized to be useful for learning. But in that first set of experiments, we didn't have a learning outcome measure. We got together, we brainstormed, and we decided, like good computational modelers, the best way of looking at this to start with was by going totally theoretical. We developed a computational model that's purpose was to represent a common formal theory about how attention and curiosity should relate to learning. So this is work that was done with Maddie Pels, who's now a graduate student at MIT, with Laura Schultz. And the purpose was to formalize theories that relate attention to learning. It's not intended to represent how we think attention and learning work. It's intended to be a starting point with which we can design other experiments and tweak it and figure out how things work. And you can think of the idea of this model as trying to explore what a rational learner or an optimal learner would look like when trying to maximize potential information gain among many possible objects in the environment. So this is not like the Goldilocks stuff where it's like, look or don't look. This is like, how do you choose between things in the world? So the ideal learner model works like this. Just like with the Goldilocks version, I'll go over this at a very high level, but I'm happy to discuss the nitty-gritty if you are interested at breaks. There is an ideal learner. That's represented by that little stick figure there. And then there's a toy world with multiple possible objects to attend to in it. And the goal of the learner is to maximize learning. There's a few other components of the model that you need to know about. One is the learning curve. So this is the part of the model that relates learning to time. This is time on this axis. This is the amount of information that you could learn about any one of those toy objects. The linking function that we chose to start with as a theory for how these things might relate is called a Gompertz. Key characteristics of it is it's characterized by a slow start. So when you first start attending to an object, it takes a little while to ramp up. And then as you start approaching everything that you could possibly learn about an object, there's a diminishing return. The other key component of the model is the information decay parameter. This is meant to encode the fact that the world that we live in is not static. If you were standing and you were learning about a bunny in a field, you could stare at it and you could learn a lot of stuff. You could learn that it's fuzzy, it's got ears, its nose does like a little cute thing, it moves like this. When you look away, you retain all of that information, but the bunny doesn't pause. It's like the bunny moves. So by nature of not looking at something, there's an amount of information lost, both due to the fact that you forget, and also due to the fact that the world isn't static. So this function is meant to capture that. And we represent this as a power law decay, which is something that people have used to represent these sort of processes in psychophysics work. Okay, and using just these components that I've described, how the model works is this. There's a decision process. At each moment, the model computes the expected information gained from each possible object. And then the ideal learner makes a decision about whether to maintain attention or to switch based on where it expects to acquire the most information. And what you get out from just those simple components is a bunch of very interesting dynamics. So I'll walk you through this. This is, again, the information that you've learned about each of the objects. In this version of the model, there's 5 possible objects, and this is time. So at time step 1, the ideal learner doesn't know anything about any of the objects, so the best thing to do is just pick randomly among the 5. Conveniently, for plotting purposes, the ideal learner picked object 1 here, and then starts to ramp up, learn about object 1, and as the learner approaches that diminishing return part of the learning curve, it now no longer makes sense to continue learning about object 1, it makes sense to switch. The ideal learner picks randomly from among the other objects, picks object 2, again convenient for plotting purposes, and begins to learn about that one. But like I described, it's like the world is not static. So while the ideal learner is learning about object 2, there's also forgetting happening about object 1. Object 2 continues to be learned about. Object 1 continues to have information lost or forgotten about. At some point, it makes sense to switch back to object 1 and then back to object 2 to maintain them. So that's the switching right here. Same thing happens for a third object and then a fourth object. Key things that you should notice about this plot that were non-obvious to us before we actually formally cashed it out. Initially, you spend more of your time with longer fixations on each of the objects, whereas over time, you start switching to more time doing small looks to each object in order to maintain those representations. Another interesting thing to notice is I made this plot so that it had 5 objects on it, but it is not the case that the learner actually gets to all 5 objects. At some point, depending upon the particular settings on that memory decay parameter, you reach a threshold and there's only so many objects that you can maintain. You might expect that an ideal learner should continue picking up things forever, that's the optimal strategy, but given the components that I described in that setup, that's actually not what's optimal. At some point, you reach capacity and you spend all of your time switching between things that you already have partially built representations rather than continuing to pick up new things forever. This thing of initially spending longer on building a representation, then switching between it, the next question that we wanted to ask is whether ideal learners do that, whether real learners do that sort of thing, which we were calling attentional juggling. I was like, do they initially spend longer looking at things and then eventually switch to switching back and forth between them to maintain them? This is an area that we've run some experiments on. Or rather, I should say, Matty Pels has run some experiments on. This is an example of just one simple setup that we run with both adults and infants. In these experiments, there's some number of things on the screen, and we're interested in looking at just the looking time, the length of the fixation to each object. What the prediction of that theoretical model said is that the look should get shorter over time, which is exactly what you see for both adults and infants in simple types of tasks where we just ask them to look at stuff as long as they want. Another area that we've been exploring that was inspired by that theoretical model is looking at how real learners choose what to pick up next. This I described as the decision process in the theoretical model. So I'll remind you again that there's this learning curve. This is all the information you could learn about an object, and this is time. Let's say you have two possible objects, object A and object B. The way that the model I described to you works is that the model picks based on the expected rate of information. I'll call that the learning rate hypothesis. So basically, that's formally here the slope of the learning curve. The idea is that given the choice between these two, you should pick object A because you expect that you can learn faster from object A than object B. The reason I should say that we started with that is that seemed to be most close to other existing theories about the relationship between attention and learning. That's not the only possible pickup decision you could have, though. So there's other things that are related to. There's other things that you could use to make this decision. For example, another theory that people have put out there is that it has to do with the gap size, so the amount of stuff you have left to learn. This is similar to sort of ideas that have been put forward by people like George Lowenstein. It could be that learners are picking based on the size of the information gap. So given a choice between A and B, you'd still choose A here, but it's based on you having a lot to learn about A and not very much to learn about B. These are often correlated, but not always. This got a little distorted, but that's okay. Another related theory that we realized is seemingly opposite of, it still is about information gap, but it makes the opposite prediction. Other people have observed that people have the most curiosity for things about which they are an intermediate amount of confident about. So if I was to ask you the answer to a trivia question and you had absolutely no idea, people have reported as like that you were not very curious about the answer to that type of question. If I ask you the answer and you are 100% sure, if you are very, very confident about the answer, you're also not very curious about that answer. You're most curious about the answer to trivia questions where you think you know the answer but you aren't quite sure. So it could be, rather than following from that, it could be that you care about this gap size, but you actually choose opposite of the largest information gap available. We'll call this the almost knowing hypothesis. It could be that you favor filling in gaps that are almost complete over ones that are much bigger. So that's another possibility that's out there in the literature. And then there's other things, for example, a sunk cost hypothesis. Probably there's a bunch of these factors that are relevant, and again, I'll get to that at the end too. How much time you've spent on something also could make a difference in whether or not you want to continue to attend to it. So with my graduate student, Shirlene Wade, she's been conducting experiments that cross these relative factors to try to test these competing hypotheses and see which things best explain human behavior. I'll tell you about one of these experiments, which I think is particularly clever. So she has a set of experiments where she created podcast stimuli, and she manipulates the amount of the story that people get, and also the rate at which they get the story. So it was recorded at some rate. We slow it by 12% or speed it up by 12%. Those amounts were chosen because they're both in the range of speeds that people can process. I don't know, is it loud enough for you guys to hear? I was like, we'll try these. We'll see if this is loud enough. I'll show you guys an example of this. Can you hear it? Okay. Oh yeah, thanks. Okay, we're going to do it again. So that was the slow rate. So even if you couldn't hear the content, then hopefully you got.
While tracking elk in the Montana mountains,
And here's the fast one.
actor Sean Penn said he fended off an attacking grizzly bear by shoving his arm into its throat to induce a gag reflex that would frighten it away.
Right. I should say, Sean Penn did not do that. These are fake news stories. So it was like we didn't want people to have encountered these stories before. Also, we ran this study on Amazon Mechanical Turk, and if it's not pretty fun, then they don't like doing it. So it turns out that if you take weird news stories and then substitute in celebrity names, people really like them. People heard things at one of two rates, and then they heard different amounts of the story as well. So I was like, I won't show you guys examples of this. So they were asked to rate their curiosity for the story after the first sentence or the second sentence or the third sentence or the fourth sentence. And then she looked to see what best predicted people's curiosity and what best predicted whether or not they wanted to continue. And to our surprise, we were really expecting rate to make a difference here because this is what most of the people who talked about these things theoretically seem to suggest was true. People were more curious in the fast condition versus the slow condition, but the effect was marginal. This is the results from the podcast study, but we run other studies where we get the same sort of thing. I was like, it trends in the right direction across a number of experiments, but it's not as predictive as we would have expected. Gap size, however, is very informative about people's curiosity ratings. So this is showing that people are very curious after sentence one when they've heard the premise and found out all of the things that they don't know. I was like, why was Sean Penn camping? Why did he attack the grizzly? And then as they get more details, they get progressively less curious. This is another way of visualizing the stages. This isn't true just of the Sean Penn story. I was like, this was true of all of the podcast stimuli that we ran. I was like, as you get more of the story, you become less curious. So the larger the gap, the greater the amount of information. This was again not just true at a population level analysis. This is curiosity at sentence 1 versus curiosity at sentence 4. If individual learners, each dot represents a different individual learner. If they were just as curious at sentence 1 versus sentence 4, you'd expect they'd all be scattered. There'd be an equal number on this side versus this side of the line, but that is not what you see. Even individual learners are more curious at the beginning after that first sentence than they are after that last sentence. This was not what we were expecting. I was like, the less you know about a story, the more interested you are. When we got the first results, I was like, we had a strong bias because of the theoretical modeling stuff to expect that rate would make a difference. This seemed really shocking to us. But then we started looking at clickbait that appears like on websites. And I don't know if you've noticed this. Clickbait generally is not designed with any sort of theoretical construct or theory of how curiosity works. But other people have noted that there's a certain type of clickbait that rises to the top. Whatever gets clicked more gets shown more. So the stuff that you see is filtered, and a lot of it has this feature that people have referred to as forward reference. So let's take this one for example. What these pilots do with dogs is one of the most brilliant things I've ever seen. It turns out to be the case that the sort of things that attract people's attention and interest are the things that create information gaps. They're the things that tell you very little about what's going to happen after you click that. So this tells you that there are pilots and they do something with dogs and it's brilliant, but that's it. A stranger approaches grandma's hospital bed. When he pulls this out, I'm destroyed. So it tells you that something exciting happened, but we know very little. Basically, the clickbait that rises to the top, although lots of stuff goes in, the stuff that ends up rising because people click on it a lot, is stuff that tells you very little, that creates a big information gap between what you currently know and what you could know, which I think is very interesting. I should say this is something that is not just useful for explaining clickbait. It's also important to understand how these dynamics work in order to design better adaptive learning systems that engage children's curiosity. Something else that we are in the process of doing with that modeling work is looking at how different cognitive abilities like might impact the dynamics and what's preferred and what's most engaging for individual learners. So if you think back to, like, for example, the memory decay parameter, the slower the slower you forget or the slower you lose information. If you're thinking about looking away from a turtle as opposed to looking away from a bunny, the total number of things that you will prefer to juggle to be optimal are different in those two cases. So adaptive learning systems, it's really important that we develop accurate models, not just because it's theoretically interesting. That's a lot of the reason that I do it, but it also serves an important function for serving as the back end for adaptive learning tools that are able to adjust depending upon the individual learner's memory decay parameter or the particular context that the learner is in. Okay, another set of work that's come from Shirlene's dissertation work that I think is very cool and I want to talk about is what to do when the gap size is hard to estimate. I started by talking about a study where we used podcast stimuli. And the reason why we started there is because news stories have a particular format called an inverted pyramid, where the first sentence tells you what it is you don't know and what the rest of the story is going to be talking about. We chose that intentionally because we wanted a case where people were able to estimate how much it was that they didn't know. But if you think about walking around the world, I was like, not everything has like a killer lead. When you're walking down the street, I was like, people aren't screaming out, you know, their news headlines. Something else that she's been working on is looking at how curiosity might work in more dynamic sort of situations. For example, this is a YouTube video. I'll show you guys this. Yeah, so how much do you not know about the rest of this cartoon? It's hard to say, right? As you're watching it, some surprising things happen. You're like, oh, it's claymation. I've learned that at the beginning. I know that it's claymation, but that's not really a gap. There's mushrooms. You know that things can pop out of the clay. They move. There's a worm. We don't know what he's going to do. Maybe nothing. Yeah, you guys get my point. So her idea was how might curiosity work in these situations where it's less clear what that gap size is. And the idea was that maybe people are able to use a heuristic to estimate gap size. One of the heuristics that's been suggested in the literature is surprise. If you're surprised, that could indicate that there's a big gap between what you currently know and how things actually work in the world. This is a plot showing you for a set of YouTube videos, the video segment, and then people's, I showed you guys the wrong plot. Actually, wait, sorry. Looks like I might have gone one step too far. Yeah, I know what this plot is there for, sorry. So this is showing that unlike with the podcast stimuli where you see a sort of steady decline as the gap is filled, people's curiosity is not well predicted by the video segment in these cases. It appears to be all over the map. The idea is that people could be using surprise in order to decide what to continue pursuing and what to abandon. And it turns out to be the case. This is people's average curiosity, and then this is average surprise. Surprise is an excellent predictor of people's curiosity and their willingness to continue looking at something. And the idea is that we're still working on in the lab is that surprise could be a heuristic for estimating gap size. I don't want to talk for too much longer. Let me wrap up this part. What I've told you in the second half that hopefully you're convinced of, but if not, I look forward to your questions during the question section, is that we have some evidence that learners exhibit attentional juggling, that initially they spend longer forming their initial representations, and then as those representations are formed, they spend more time switching back and forth to maintain representations. We were very surprised to learn that learners' curiosity appears to be better predicted by knowledge gap than by rate, at least in the experiments that we've seen, and that's something else that we can talk about in the question part. Also, when it is difficult to estimate the gap size, surprise could stand in for that. Surprise, we know, triggers curiosity and could possibly be a heuristic to estimate information gap size. I want to end by talking about, well, I'm going to do two more things, and then I will take questions. The first one is I want to talk about another set of work done by another graduate student, Louis Marti, who has been working on the metacognitive aspects of this process. So when you think about gap size and estimating information gap size and that driving what you're interested in, it becomes clear that that is metacognition, and understanding how those processes function and drive what you attend to is very important, especially when you think about that first topic that I talked about, which is that these processes guide the acquisition of knowledge. One thing that he's been interested in particular is certainty. So metacognition is involved in detecting a knowledge gap. You have to know what you don't know, but people don't always know what they don't know, and this is something that has been a source of inspiration for him. He got interested in science initially because he got interested in the skeptic movement, and he is especially interested in understanding why people can be very confident about things that are not right. He has a series of work that I'm not going to have time to get into the details, but the paper just got accepted in Open Mind, and I'd be happy to discuss it at breaks, about people's certainty and where it comes from. And what he's found out, this is the nutshell version, is that human certainty is not well calibrated to the evidence at all. We knew that it wasn't going to be perfectly well calibrated. We expected better than what we saw. Interestingly, the best predictor of human certainty is not how certain you should be given the evidence, but whether or not whatever mental model you are using, whether or not that's working, it's your feedback. So if you keep getting things right, if things keep working, you're confident that you have the right idea, even if you shouldn't be. Yeah, so that's interesting, and maybe a topic that is of interest to you guys, and you should stop me and ask me about it if yes. The last thing I want to do is end by talking about what we still don't know about curiosity. In particular, I think there's two big questions that it is very important that we figure out. The first one, and this is probably like the most common question I get asked by like popular media places. People ask me, how can we make sure that adults maintain curiosity throughout the lifetime? How do we get people to have the same sort of curiosity that a baby has? I do not like this question because it has a presupposition that I do not agree with, which is that babies are more curious than adults. That's so taken as a given. Yes, nobody ever asked me if that's true. That's just assumed. I know what people are talking about. I have a baby, and if you give him almost anything, I was like, your keys, a bottle cap, I was like, this is a lantern thing, he is interested in it. I think that question is coming from observing that babies are sort of interested in anything that you put in front of them. What I want to emphasize that we don't know yet is we do not know whether or not that is because my baby has a higher drive, is more curious than an adult, or whether it might actually be the case that my baby just knows a lot less. My baby is dumber. He doesn't know how things work in the world. What I've just talked to you about, a running theme that I hope came through, is that what you're interested in has a lot to do with what you already know and what you already understand. If you think about babies as knowing nothing, what you'd predict from that is that they should have sort of uniform interests about anything that you put in front of them in the world. It's all, just like the ideal learner model in the attentional switching version of Maddie Pelz's work, it doesn't matter what they choose. Anything you put in front of them, they're going to be able to gain as much traction on as anything else because they're not starting from a place where they know anything. What could be the difference between babies and adults is as you grow up, as you learn stuff, as you start building up these complicated systems of knowledge about particular topics, it could be that your curiosity doesn't diminish, but rather it becomes more peaky. You're interested in maintaining representations about learning more about the things that you already know something about, rather than learning about anything that you possibly could learn about in the world. So this is something that I think is likely, I suspect is right. I don't think that we were able to look at it 20 years ago, but now there's Google. There's all sorts of measures of people's interests in real-world situations that we didn't have access to before. I think that this is an understudied area that should be of interest to us, that nobody's gone there yet, and I think that we should. Another thing that I get asked a lot is, like, there's an assumption in a lot of the literature, especially the education literature, but other ones as well, that curiosity leads to enhanced learning. There is some evidence that curiosity leads to enhanced learning, but there's not that much, and there's far less than most people think. There's a lot of papers that report that curiosity leads to enhanced learning. But again, going back to that theme of you having curiosity that is prompted by what you already know, there's another direction that people don't consider, which is the opposite one. We know that when information is ripe for learning, you are more curious about it. A lot of the papers that purport to show this may actually be showing this. This is not something that I think people are as aware of. This is also related to work that Shirlene Wade has been working on. When we started running it, we were expecting to show that everything was this, and actually, to our surprise, it looks like there's independent effects of both. Curiosity, you are more curious when you're on the verge of knowing stuff, as in a trivia question, but also there appears to be enhanced learning for stuff that you were curious about, and also learning of irrelevant material when you're in a curious state. Curiosity is a state and trait. Both of those are independent things. So it's like there's probably some of both of these things going on. Okay, in the interest of having time for questions, I will end there. Thank you guys so much for having me. Thank you to all the members of my lab and the people who gave me money to do this work. Thanks.